Okay, so on this lesson, we're going to be looking at logarithms. It's just an introduction, and then we'll get into logarithm transformations later on. So first thing, a logarithm is something that you can use to rewrite an exponential, and then vice versa. If you have an exponential, you can rewrite it as a log. So a logarithm is the power exponent to which a value must be raised to equal some other value. So for example, if we look at this here, this is the same thing as this is a base raised to this power equals this. So notice b to the x equals a. So this is called a logarithm. It has a log. So to read this, so you might write it on your notes, to read that you would say log base b of a equals x. So that's how you would read that. So again, a log is another way of writing an exponential, and then an exponential is another way of writing a log. So I like to call this part of it the base raised to this power. I like to call it around the world. So then it's the same thing down there. So we're going to be just rewriting these from logarithmic equation form to exponential form. So again, this is called the base on a logarithm. So the base of your logarithm will become your base of your exponential. So 2 raised to this power, so the third, equals this number, 8. Notice that's true. 2 cubed, 2 times 2 times 2 is 8. So again, these are equal to each other. Those mean the same exact thing. So then we're rewriting this one. The base is 9 on the log, which becomes the base of your exponential raised to this power, 2 equals 81. Again, those are equal to each other. 9 squared is 81. Next one, this is the base, 16 raised to this power, 1/2 equals 4. Remember when we talked about radicals, anytime something's raised to the 1/2, it means you're taking the square root. Notice the square root of 16 equals 4. Okay, so now there's some special logarithms that we're going to be seeing. There's one that's called a common log, which has a base of 10, and usually the log does not have the base there, so that's just an understood 10 for your base. Okay, so again, this is what it will look like. It won't actually have the little base there, so you're going to have to know that's a 10 there. That's called a common log. Okay, the other special log we have is a natural log. So a natural log has a base of e, which we've been talking about, Euler's number. So it's like pi, a constant. Okay, so anytime I have a natural log, it's going to say ln. This is what it's going to look like, which is the same thing as what's over here. So it's not going to have the little e here as your base. You're going to have to know when it says ln, that means natural log, and the base is e. So these are two special logarithms that we're going to be seeing that you're going to have to know that if it just says ln of x, that means the base is e. Okay, so Euler's number e is approximately 2.71828, and so on. Okay, it is the value that the expression 1 plus 1 over n raised to n approaches the value at n infinitely. Okay, so it just means it keeps going and going and going and going. All right, so this next part, we're going to rewrite the log equations in exponential form. So notice this just has an log with no little subscript base. So that's called a common log. The base is 10, which will be your base, raised to that power, 2 equals 100, which is true. 10 times 10, 100. Notice this one has an ln, which means the original base is e, raised to this power, 3 equals e cubed. Notice this one has ln, which means the base is e, raised to the 6th power equals that decimal. So here we're just rewriting these. This one just says log, no base, which means common log, base 10, raised to the negative 1 equals 1/10. We actually talked about this yesterday on the last lesson. If I have a negative exponent, I would take it and move it to the bottom, and it would become 1 over 10 to the first, which is 1/10. Okay, so these first examples that we've been going over, these were just rewriting. We're just rewriting to a different form. So logarithm is used to rewrite an exponential, and then, or vice versa. Exponential, you can write it as a log. Okay, next part, we're going to be rewriting the exponential. Now we're given the exponential, we're going to write it as a log. So I do it very similarly. I start with my base of my exponential. I need to write log first. The base of my exponential is my base, the little subscript of your log. And then I go to this, so I'm going to call it around the world. So my base, and then of log base 25 of 5 equals 1/2. So it should be the opposite. So base is 25 to the 1/2 equals 5. So notice it gives me the same thing. So always start with your base. Begin with B. So this one, I'm going to have log. My base on this one is 10. So actually this is a common log. So I'm going to go ahead and write the 10, and then I'll show you need to get rid of it. So 10, base 10 of 1 over 1,000 equals -3. So you would write it as log of 1 over 1,000, because anytime your base is 10, that's a common log, and so it's just understood that you wouldn't put a 10 there. This one, start with your base. My base is 2, so log base 2 of 16 equals the exponent 4. So a logarithm always equals the exponent. So again, no matter which way you're going, from log to exponential, exponential, log, you're going to use around the world and always begin with the base. This one, notice my base is E. So if my base is E, I need to write it as a natural log. If you want, you can write E for now, of 7.389 equals 2. So I would write it as natural log of 7.389 equals 2. So again, common log has a base of 10, natural log has a base of E. So you would write it as, instead of log, you would put natural log ln. Okay, so those 3 different types of examples we were just rewriting. Now we're going to be evaluating without using a calculator. So we're first going to rewrite the expression, and then rewrite it in exponential form, and then we're going to determine the exponent. So I'm going to rewrite this. So it says evaluate the logarithm. We're trying to find what it equals without a calculator. So I'm going to rewrite it like I was doing. So we're trying to look for this. So my base is 5, so that becomes my base of my exponential. I'm looking for my x, which is my exponent, equals 125. So when you evaluate a log, you're trying to find the exponent. So I'm trying to find what x would be. So start with 1. 5 to the first power is 5. That doesn't give me 125. 5 squared is 25, so it wouldn't be 2. Go to 3. 5 cubed, 5 times 5, 25 times 5 is 125. So my x would be 3. We're looking for the exponent. So we're not using a calculator on these. Okay, so my next one. Trying to find what it equals. So my base is 6. So my base of my exponential is 6 raised to the x equals 1 over 36. Okay, so anytime I go from a whole number to, if that's a fraction, we know we're going to have a negative exponent. So my x is going to have to be negative. So I want you to, for now, cover up the 1 and just look at the 36 in the bottom. What would I have to do to 6 to get 36? I would have to square it, 6 times 6. So my x would have to be -2. So 6 to the -2, we'll just work it out. You'd have to bring it down, which would give me 1 over 36. So if this is a fraction, we know we're going to have a negative exponent. And then just cover up the 1 on top, look at only this piece, see what you would have to raise that number to get that bottom number. Okay, so next one, notice there's no base here, which this means it's a common log, 10, base of 10. You have to know that. So I'm trying to find 10 to what power gives me 10,000. So I would just start with 1. 10 to the first is just 10. 10 squared is 100. Actually, you could probably just count the zeros. 1, 2, 3, 4. So that would be x equals 4. So 10 to the 4th power, because you're going to need 4 zeros there. Okay, next one, I have my base of 8. I'm trying to find my exponent when we evaluate a log equals 64. So 8 squared gives me 64. So x would be 2. So those are evaluating them without using a calculator. Now, of course, there's going to be some times when my exponent is not a whole number. So there is a way to change the base in order to evaluate it using a calculator, okay? So if we look at it here, so we would be looking 5 to what power would give me 250? Well, that's clearly a decimal, okay? So you can use change a base formula by using a common log. So you would take the common log of 250, divide it by the common log of your original base. Now, the calculators that we use in our class, we actually can change our base. Some calculators you can't. So if you can't change the base on your calculator, then you're going to have to use change a base, which is taking the log of the top, or the 250, and then the log of the bottom, okay? Now, in this case, I actually can change it. So I'm going to do it both ways. So first going to use the change of base. So I'm going to take common log of this number, 10, over the common log of your base. So a great way to remember your change of base formula is the base goes in the bottom. So the base was 2, it goes in the bottom, okay? So the reason I'm doing this is because, actually I don't want to do that. On my calculator, now a great way to check it, because remember we were doing these up above without using a calculator. We were trying to find 2 raised to what power would give me a 10. If I use the calculator, I can go back and do 2 raised to that answer, and it should give me 10. So that's a great way of checking it. Now, so the reason we're using change of base here is because we weren't able to change the base on the calculator. However, there is a way to do that, and I'm going to show you that on the back of this page. But right now, let's go ahead and use the change of base formula. So we're trying to find on the next one, 20 to what power gives me 450. Well, again, we can't do that. That's in our head. That's a decimal. So what you would do is take the common log of 450 divided by the common log of 20. And remember, the great way to remember it is the base goes in the bottom, so the 20 will go in the bottom. So using a calculator, you're doing common log of 450 divided by the common log of 20. So you get 2.039. It says to round to 4 decimal places. Great way to check it. If you go back to your calculator, you are doing 20 raised to that power. I want that whole decimal, so second, and then your answer, which is the negative symbol. And then notice it gives me the 450. So that's a great way of checking those. okay? All right, next one. So I'm going to take the log of 15.7 over the log of 0.9. Again, a great way to remember your change of base formula to evaluate it. If you are using a calculator, base goes in the bottom. So when you type that in the calculator, you should get negative 26.1356. Next one, log of 80,000 over log of 16. Remember, base goes in the bottom. So that would be 4.0719. So this is one way, if you aren't able to change your base on the calculator, this is one way to evaluate a log with using a calculator. So again, I'll show you in a few minutes on how we can change that base. So let's flip over. Okay, so on the back, we're going to be looking at inverse properties. Remember, inverses undo each other. So the inverse of an exponential, which is, remember, x is in the exponent, function is a logarithmic function. So vice versa, a logarithmic function is an exponential. The inverse. Okay, so exponential and logarithmic functions undo each other because they are inverses. So notice right here, this inverse property can be used to simplify exponentials or logarithmic expressions and are useful for solving exponential and logarithmic equations, which we'll eventually get to that point. So notice right here, this b is raised to the x, which equals b to the x. So if we were to write this, this base is the same as this log base, so they actually cancel and it just gives you that x there. So if we look at this, these are not hard. The base of this log in the exponent spot is 10, which will cancel with this base of 10. So my answer would just be 3x over 4. This base of this natural log is e, which is the same base as that, so it would just be x plus 2. This base here is the same as this e, so it would just be 5x. This base is the same as this log base 2, which is 7x plus 8. So they're undoing each other. This log of 0.1 is the same as this 0.1, so 12x. This 1/2 base is the same as this log 0.5, which is just x. Log base 2, negative x over 7. Log base 10, it's not written, it's a common log. Base 10 here, they cancel each other, and you're left with x minus 9. So you're just using those inverse properties to cancel out and simplify. Okay, so now we're going to graph a log on the calculator just to see what it looks like. We're going to use a graphing calculator. You can either use change a base, or I'm about to show you how you can change your base on the calculator. So let's go to y equals, because I'm going to have to graph it. We're going to find the log button. Now, this is only a common log. If you notice on the example on our notes, it's log base 2 of x. So I'm going to go to the math button. And if you go down, notice it says on A, log base. So I'm going to go ahead and press that A there. Notice it gives me a log, and I can put whatever base I want. So I want the base of this log to be 2, and I'm taking log base 2 of x. So put an x there. That's exactly what we have here. We're going to go to the table, and then notice there's lots of errors here. So we're going to plug in or write down our points from the table. When you plug in a -1, notice it says error, which means undefined. 0 is also error, so undefined, which means it won't be crossing that. 1 is 0. 2 is 1. 3 is 1.585. 4 is 2, and 5 is 2.32, we'll round 2. So there's my points. So again, to go to the calculator, you can either put it in change of base, log of x over log of 2, but I just showed you how to change your base. So math, and you're going to go to A, which is log base. And you can type whatever log you want. All right, so if we want, we can also go ahead and press graph, so that way we can kind of see what it looks like. Notice it's going to be approaching a vertical asymptote, which is the opposite of exponential. So when x is -1, it's undefined, which means I can't graph it. Same thing on the 0. 1 would be 0. 2 would be 1. 3 would be 1 and a 0.585. 4, 2. 5, 2.23. So graphing it, it's actually approaching there. So the domain, notice that it's including only positive x values and it doesn't include 0. So x is greater than 0. The range, notice it's continuous going down and up, so all real numbers. If you remember from exponential, the domain was always all real numbers. This is the opposite. On the logarithm, they're inverses. On a log, the range is all real numbers. Notice we do have an x-intercept here. It's at 1, 0. And then notice we do not have a y-intercept, which is the opposite of what our exponential was. Exponential, we didn't have an x, but we did have a y-intercept. Asymptote, on the exponential, we had a horizontal, but this one we have a vertical. So it's crossing the x. It's a vertical line crossing the x at 0. So these are inverses. A log and an exponential graph are inverses of each other. So again, you can either, on this, use change of base, which I wouldn't see why you would do that, but you can. Not all calculators will allow you to change the base on a log. So it's just usually common log and natural log. So since you're using these calculators, you can actually go in and change that base. If you have any questions, please let me know.